The Mass Spectrometer. Tremendously useful piece of kit here. It allows you to measure the mass of ions. It allows you to work out the relative abundance of those ions. So you can work out the proportion of a particular isotope of chlorine that you have in your mixture. For example, it allows you to analyze large molecules like proteins, for example. So let's look at how the mass spectrometer does what it does. This is a very simplified diagram. So I'm missing, for example, the way we make the ions, but what we have is, to begin with, we make our ions and then we accelerate them. So we have applied a PD between these plates and our ions will be accelerated in this direction. So, having accelerated them, we then have a range of velocities coming out of here, and what we want is a single velocity, no particles with any other velocity other than our chosen velocity coming through here. So here we have an electric field, and at right angles to that we have a magnetic field. And we choose the strength of the field, the electric field, and the flux density of the magnetic field so that the two effects exactly balance, and so the particles will come through here undeflected. More detail on the maths of that in a couple of minutes, but we have a section of our mass spectrometer which accelerates our ions, having made our ions in the first place. We then have a velocity selector here, and this works by having these crossed fields, we call them. In this case, I have my magnetic field into the page and I have my electric field vertically. And if we choose those fields correctly so that the particles come through here undeflected, they will all have the same velocity. And here we are choosing our velocity. If they're too fast or too slow, they will hit this barrier just right, they'll come through the gap. So we have accelerated them, we have selected our velocity, and then we have our deflection chamber. So our beam of ions enters our deflection chamber, and in the deflection chamber we have another uniform magnetic field. And by Fleming's left-hand rule, this will cause our beam of ions to bend. But the amount that they bend depends on their mass. Again, we'll do the maths in a moment or two. So this is basically how your mass spectrometer works. We make our ions, we accelerate our ions, we choose the velocity of our ions, and then we cause the ions to bend in a known magnetic field called the path of the ions to bend, I should say, in a known magnetic field, and they strike a photographic plate here. So here we have the slit. If we look back at the chamber, here's our gap here, and that's what that is. So our ions have come in, they've been bent, or the direction of them has been bent by this uniform magnetic field, but here we have two different positions that our ions have arrived at on our photographic paper, which indicates two different masses. And notice I have labelled the distance from here to here as twice the radius for the first ion, and here to here twice the radius of orbit for the second ion, because what you have here is the diameter of the circle that these ions are performing. If I take you back to my chamber and my beam, you can see that this distance is the diameter of the circle, not the radius. That's an important point, particularly for answering questions. So there you have the mass spectrometer overview, really. Let's look then at the maths of this. So we're going to accelerate our ions. Our ions will have a charge Q. Those ions are entering a field, an electric field with a region, electric field strength E. And we know that the force on here, on our charge, F equals EQ, which of course equals MA. So we have an acceleration then on our particle by, or our ion, by Newton's second law, equal to EQ over M, or V over D. Times Q over M. So here we have the acceleration. Then the velocity selector. Well, you have crossed fields. That is to say, you have the electric field, EQ, and you have a magnetic field, which gives us a force BVQ. Now, what we're doing is we're saying that the force, let's say, up on our particle is being exactly balanced by the force down, the up by the electric field and the down by the magnetic field. And so we're saying EQ equals BVQ. So V then is E over B. That's quite important for us. So when our particles leave our velocity selector, we have chosen our fields so that the particle goes through undeflected, so that we have a single velocity leaving the velocity selector. If the velocity is too low, then BVQ will not equal EQ, and the particle will go up and miss the slot. Conversely, if the velocity is too high, then the magnetic force is greater than the electric force, and so it goes down and misses the slot again. So we are choosing our velocity by using our crossed fields. That's a term you should be familiar with. And then we have our deflection. So we now have our particle with a charge Q in a region of magnetic flux density B, traveling with velocity V. And so we have a force on it, BVQ. And of course, this is a centripetal force, in that the force is at right angles to the motion, Fleming's left-hand rule. So that equals mv squared over r. So now we have BVQ equals mv squared over r. That cancels with that. And we have r equals mv over bq. That is to say, r is proportional to m, because all the rest of this we've chosen. So we have the radius of the orbit, the radius of the circle that these particles will perform in the magnetic field is proportional to the mass of the particle, and therefore you can work out the mass.